Let us take AC with L, C and R. All the three. The circuit diagram is something like this. R, say this is R, this is L and this is C. We have components like this, and we have E is equal to E naught sine of omega t. This is the property of the source. You can call it as a supply also. Now, what happens? In order to understand what happens, we must plot the phasor diagram for each component. So let us try to understand. See, this is the direction for current. In case of R, what is the direction of potential drop across R? Same phase, so ER. What will be there for inductor? It is EL. And what will be there for we have like this. You can also show it the other way. You can make it C here, you can make it L here, makes no difference, because again they are in opposite direction. That is what is required. It is not important negative y-axis or positive y-axis, that is not important. What is important is to represent the two potential drops in opposite direction, because in one case the current and the applied voltage, they are having 90-degree lag, in the other case lead. So lag and lead is represented by this particular directions. Now how to find the resultant here? To find the resultant here, what we can do is, I think you are aware of how to find resultant of vectors. Apply vector analysis here. We see that these two are in opposite direction. So when we try to find the resultant, we will write it as EL minus EC. This is in opposite direction. So we have this. Then what we have? We have ER this way and I is in this direction. See, this is how the system can be reduced. Now in this case, what will be the resultant? So the resultant will be somewhere like this. This is your. So how to find the resultant now? Complete the triangle. This is your phase difference. This is how we can identify. So what we have the resultant now? So what we can say? EC square is equal to EL minus EC the whole square plus ER square. So what we can write this as? ER is what? I into R the whole square plus I into XL minus I into XC the whole square. We can write like this. You can write this way also. You can write I naught also. You can write I naught here, I naught here. In any case, it is getting cancelled out. So what we have now? I naught square comes out R square plus XL minus XC the whole square. See, something like this we are getting. Correct. So we have what here? I naught square Z square. So what do we get now? Finally, Z square or Z is equal to root of R square plus XL minus XC the whole square. See, this is the impedance of a LCR circuit. In the exams, they will give you LCR circuit. LCR circuit means Z will be like this. Now students, this can be XC minus XL also. It makes no difference because it is whole square anyway, na? So whether you take a minus b whole square or b minus a whole square, you will get the same value, right? Now, but it makes a difference in case of tan phi, because if you take xl minus xc or xc minus xl, one of the expression will become negative. So the angle phi will go into different quadrant. So this is what we get as it. Now let us try to find this angle phi. So from the impedance triangle, tan phi will be what? Tan phi will be this side, which is EL minus EC. EL minus EC upon ER. This is what we get. So EL is, again we know, we have seen all the previous xi, the derivations. I into XL, I into XC, these things are known to you by now. So we can say tan phi comes out as XL minus XC upon R. See, this is how we can find out the angle by which the current would lead or lag. See, here we cannot say whether it is lag or lead. Then how will you identify what is happening to the current? Now see how to find the expression for current. So what will be the current? The current equation. What will be the current equation? I will be given as I naught sine of omega t. Now please tell me whether it will be plus phi or minus phi. We cannot say. That is why we will write it as plus minus phi. So the question arises, if we see this plus and minus, many questions arise in our mind. It should arise. If it is not, please force yourself to think. How, what to think? How can the current lag and lead together? How can the current lag as well as lead simultaneously? That is why I told you, please think. Plus minus is written, na? Either lag or lead will be is understood, but here we have written plus minus. So the answer lies in this expression. Answer lies in the expression. How? There is a minus sign. So what we can say, either XL is greater than XC or XL is less than XC. That will depend upon the data. What is XL? XL is omega L. Omega L is what? 2 pi FL. So XL depends on the value of F. XL depends on the value of L. Now it is possible that XC, which is 1 by omega C. So there is a possibility that XL is greater than XC. So how to find out that? See, in order to identify what is the expression for the current, whether it is plus phi or minus phi, and eventually conclude whether it is a capacitive circuit, whether it is a inductive circuit, that identification happens by taking this equation into consideration. So what we have is, if XL is greater than XC, XL is greater than XC, what we have? Tan phi is, we can say, positive. Tan phi is positive means what? It means if XL is greater than XC, the conclusion is it is inductive circuit. It is inductive circuit. Why do we say it is inductive circuit? Although three components are there in the circuit, na? R is also there, L is also there, C is also there. But then we are classifying it is inductive. Why? Because inductive reactance is greater than capacitive reactance. Please understand. It's a highly conceptual thing. The value, you cannot compare the value of L, C and R. Wrong. This is a disaster. You cannot compare the value. L will be given 10 millihenry, C is given as 5 microfarad, R is given 100 ohms. Doesn't mean that 100 is greater than all those things, so you will say it is resistive. Wrong. That is not the way of which you are going to compare. We have to compare similar properties. Similar properties. What is the property which is similar to all the three? resistance property is similar to all of them. So resistance value is 100 ohm. Get the equivalent resistance of C in ohms, that is called capacitive reactance. Find the value of 1 by omega C. The unit of 1 by omega C capacitive reactance will be in ohm. Now 1 by omega C can be compared with R, not C with R. Not C with R. Similarly, L, the resistance offered by inductor is known as what? Inductive reactance. So omega L, that omega L will be measured in ohms. Now the 3 are in ohms, now compare the 3. That can be done. Not that you blindly compare L, C and R. No. It is possible that inductive reactance is more than the capacitive reactance, which means that the resistance offered by an inductor is greater than the resistance offered by the capacitor. Therefore, the circuit is predominantly behaving as an inductive circuit, because the effect of inductor is more dominant than all other components. That is why the circuit will behave as a inductive circuit. So in inductive circuit, tell me what is the expression for the current? In an inductive circuit, we know the expression for current is given as I is equal to I naught sine of omega t minus phi. So therefore here the expression for current will take the shape of sine of omega t minus phi. See the kind of concept which is involved. Concept is there, but the expression is very easy to write. That is. Now there is one more case. The other case is what? If XC is greater than XL. If XC means that the resistance offered by the capacitor is greater than the resistance offered by other components in the circuit, then we will say this will behave as a capacitive circuit. Although there are 3 components, but the behavior, the effect of capacitor dominates the effect of other components. So the expression for the current will reflect this particular dominant property of capacitor. Now in a capacitive circuit, what exactly is the phase difference? We know that current leads. Current leads. So your tan phi will become what? Negative. Tan phi will become negative because XC is greater than XL. So XL is smaller than XC. So this will become negative. This gives us an indication what kind of circuit it is, because these are the fundamentals of solving any question from AC circuit. Many type of questions are framed. Predict the nature of the circuit. Identify the 2 components, like that questions will be there. That time you will face difficulty. Please understand, that is why right now. So capacitive circuit, I is equal to I naught sine of omega t plus phi. The value of phi will be calculated from this. Remember that. That is exactly how capacitive circuit can be identified and distinguished from inductive circuit. Power consumption. This is about the expression. So we have seen what? We have seen the expression for the net resistance, which is known as impedance. When you are reading also, students, don't take these things very lightly. This will give you the worst nightmare when you will solve the numericals. So reading also, don't just read some, don't give some name to these terms. Give it proper wordings. Net resistance, don't call it resistance. Then how will this and this R be different then? And this will be the root of committing mistakes in the exam. Be very careful. Don't call this as resistance. This is not resistance. This is net resistance. There is a difference. Identify. This is high time. You need to identify between the difference between the words. Now we know what is the impedance. Correct. First thing we come to know. Second, we know the structure of impedance triangle. Correct. We know what is the phase difference. Then we know expression for current. That is the general expression. These are specific expression related to the kind of LCR circuit. All LCR circuit will not be inductive. All LCR circuits will not be capacitive. It may be different depending on value of XL, XC. Now what about the power consumption? The last thing. Expression for current, this we have seen in LR circuit. Expression for the current, this one we have seen in RC circuit. So the power consumption will be similar. The power consumption is going to remain the same as we have seen in case of LR circuit or RC circuit. So power consumption, just I will write the expression. Again, I expect you will be solving it as a matter of practice for you. Power consumption, again the same old story, instantaneous power P is E into I, so we will write E naught sine omega t and I naught sine of omega t plus or minus phi I will write. Now the equation is same as what we had seen in the previous two combination circuits, right? So therefore I will write directly the expression for average power. This is ERMS IRMS into cos phi. So we have a power factor there. So cos phi is known as power factor. Power factor cos phi is R by Z. Universal. Z will depend upon what all components are there in the given AC circuit. That is exactly how any AC circuit can be analyzed. Now the most important part of this. Most of the students have this query in mind, how to remember so many equations. There is no need to remember anything if you have understood one point in this. That is, phase difference, if it is known to you, if you are able to draw this diagram for RC or for RL or for RLC, in all the combination we have taken this as our base of analysis, and Pythagoras theorem you are doing from childhood. So what is left out? New concept here. So why there is a necessity to remember anything? If you know how to find resultant of this, finished, you know everything. That is why don't stress yourself to remember the equation, because this is not the end of physics. You will have million equations to remember them. It is better you understand how exactly the equations are extracted from the given situation. This is one method which is called conceptual method. Second method is, let us say, your method. Normally what you do. Remember this equation. The second method I am telling you. Remember this equation first. Second, this. And third, the expression for current. That's all. For all the circuit diagrams, this is equally applicable. How? See, first circuit, if you remember, we did R only. Remove this, remove this. So Z is equal to R. So tan phi is what? This is not there, this is 0. That is why phase difference is 0. See, they are in same phase. Power consumption. Phi is 0, cos 0 is 1. ERMS, see, we got it for R only. Like that for all combination you can get it. Let us say the second circuit which was L only. In L only means R is not there, C is not there. Drop it. So your Z is XL. So tan phi is XL by R. We have derived it. And XL by R. The phase difference is 90 degree. Cos 90 is 0. Power is 0. See. Every equation is contained in this equation. So if you remember this equation also, fair enough. Now let us say RL circuit. There are two components R and L. Drop the C. Drop this C. So you say R square plus XL square. Correct. And what is tan phi there? Drop the C. EL by R. So XL by R. Correct. See, everything we get it from this equation. That is why read when you are doing these derivations, when you please write the equations derivation once. It is very essential. If you think by reading it you can get it, you are little bit, optimistic in that case. So the equations, these Z and tan phi and average power, only three equations are required for solving any numerical from LCR circuit. Got it? Well, students, I think you were wondering a combination of circuits when we took RL, we took RC, then why didn't we discuss LC? Correct. This is where I initiate the thought process in the students. This is how I initiate, because unless until you start thinking, definitely numericals in physics will be little bit tough or uphill, and that is why you label this numericals are difficult, because you don't think. Please think now. Start thinking. L and C. Correct. What is the phasor relationship between current and, let us say EL we have 90 degree. What can you say about C? 90 degree. Correct? Is there a R here? There is no R. Now tell me what will happen. What will happen is very simple. The charge, because of 90 degree lag this way, because of 90 degree lead this way, it goes this way only. Where is the R to push it? Is there the component which will push? Otherwise we were showing in this direction ER. In that direction the charge was experiencing a push. So it was advancing in the circuit. And when the charge advances in a circuit, that constitutes current. In your childhood you have studied this. Rate of the electric current is nothing but charge in motion. But here you see, is the charge moving in that direction? No. That is why what we conclude, the charge will oscillate. So LC circuit is an oscillatory circuit. That is exactly how we can conclude from this. This is what is required. This is the skill you have to develop to draw conclusion from the diagrams. If everything is given to you, everybody will read that, then how are you different from the set of people who are selected in the entrance exam? Show your skill that you are different. How? Your analytical skills of analyzing the given situation keeps you apart from the crowd. Now let us analyze this situation. This is the practical meaning of AC with LR circuit. LC circuit. Now let us see how exactly this happens. If we say that it is an oscillatory circuit, then the next question comes to our mind is, which should come to our mind is, what is the time period? If there is oscillation, there has to be a time period. Then what is the time period? How to find that? What is the frequency? So many questions arise. So let us analyze this. Say we have this is C, this is L. We have connected a source like this. This is a two-way switch. Please understand this. This is a two-way switch. Now, if I connect both of them to the source, what is the nature of connection? How are we placed the two? The two are placed in parallel to the source. See, if you connect all, the two are in parallel. In parallel, what remains constant? We know potential difference remains constant. So we can say potential drop across L should be equal to potential drop across, because V remains constant in parallel circuit. VL is what? V is E is equal to minus of L di by dt. So minus of L di by dt we can write. This can also be written as VC. V is what? Q by C. Q is equal to C into V. You have done this in capacitors. So V will be what? Q by C. Now see what we can write. Di by dt is equal to minus of 1 by LC into Q. Correct? By simply rearranging the term. What is I? I can also be written as dq by dt. This is minus of 1 by LC into Q. This is how we can write. So what is d by dt of dq by dt? Second derivative of charge. So what we got? Have you ever come across such an equation? This equation is similar to an oscillatory equation. If you remember, in oscillations you have done in simple harmonic motion. I guess you have done something like this. This is the simple harmonic equation where we said acceleration, second derivative of displacement is acceleration, is equal to minus omega square y. See, please try to correlate it this way. Whatever we have here, the same we should have here. This is how the correlation happens. And it should be second derivative with respect to time. Compare it. So d square q by dt square is minus 1 by LC into Q. Compare. So by comparing, what we can say? The charge is oscillating. See here, Y, Q. So the charge is oscillating. So what is the time period? Compare. So by comparison, omega square is 1 by LC. So omega is 1 by root LC. What is omega? Omega is 2 pi by T, we can say. This we get as 1 by root LC. So T is equal to 2 pi root LC. This is what we can say. This is the time period of oscillation. Or you can say frequency F is 1 by 2 pi root LC. Anything. See how we can find out. See from where the correlation went, it was the phase. See the interpretation, the analysis started from the basic information that we know. Inductor 90 degree out of phase, capacitor 90 degree out of phase. So we got resultant. We said that it is an oscillatory. So we started, since it is parallel, so we can say that voltage will remain same. This is exactly how we can find. Where do we see this oscillatory circuits? These oscillatory circuits, that is LC circuit, is very commonly used in radio. The frequency adjustments, you do adjustments of frequency, different radio stations have different frequency. How do we adjust that frequency? How are we able to receive those waves? They are all done by an LC oscillator. So the LC oscillator, the function of it is, see, charge is oscillating, If we try to analyze this situation, we got what? The frequency, right? If you have any idea, the radio stations are also, characteristic property of radio station is what? Frequency, hertz, Different FMs you see FMs. What is the meaning of that FM? There also you see, technique is involved. So frequency. We are using the frequency. Why? Because they are based on this. Every frequency can be altered here. See, in the room where you are sitting, many frequency waves will be there. All the frequency, you talk of BBC waves, you talk of All India Radio, you talk of any radio station waves, you will have characteristic frequency. Now what happens is, if I make my LC circuit, my oscillator, if I force the charge to oscillate at the same frequency, then what happens is, the energy of the charge will be converted into sound wave and we hear that radio station. See, that is exactly how the design happens of radio, or how we are using LC circuit in daily life. So it is not confined to the books. This has extensive real life applications. If we know how to use these equations, this is where you become technologist. Now this is about the LC circuit. So if an LC circuit is there, see, again you will get this kind of derivation. In the board exam also they'll ask you, derive the expression F is equal to 1 by under root LC, where the symbols have usual notation. This kind of questions are very commonly asked in the board exam. Okay. Now what happens is, in the choice, in your board paper, you will have choice. And in the choice, there are two kinds of question. One will be derivation oriented and one will be theoretical. Now what happens is, most of the students select the theoretical question so that they can write a big essay on the answer. In my opinion, if you go for the derivation part, you can get full marks out of it, because derivation will involve all mathematical calculations and steps, and there you cannot lose marks. But if you are going for a theoretical reasoning essay type of question, there might be some loss of marks there, remember. So choice is yours. Absolutely, I cannot stress on you, you write this way, that way only. But mathematical one will always fetch you more marks. That is about your different kinds of circuits that we have in case of LCR combination. Series resonant circuit. What is the meaning? Now if you have concentrated, if you had followed every step till now, then you will definitely make out what is series resonant circuit. Why? I'll tell you that. See, we had derived an equation in an LCR circuit. What is the equation? That tan phi is equal to XL minus XC by R. This is what we have derived. After that we analyzed like this. If XL is greater than XC, we said it is inductive circuit. We said if XL is less than XC, that is XC is greater than XL, we said it is capacitive. So the question arises, what happens if they are equal? Less than and greater than, fine, we had discussed everything about it. Now the time has come for XL is equal to XC, that is called a resonant circuit. If XL is equal to XC, so in the numericals, if it is given to you in a series resonant circuit, it implies XL is equal to XC. So please remember. So if XL is equal to XC, please understand this, L is not equal to C, XL equal to XC. L can never be equal to C. L is an inductor which will be measured in henries, and C is capacitor which is measured in farads. How can the two be same? But their behavior towards the source can be same. And what is that behavior? Reactance. Inductive reactance, which is omega L, can be equal to capacitive reactance. That is possible because both of them are measured in ohms. So XL is equal to XC means what? This is the case of resonance. So resonance in an electrical circuit. So don't think there is some sound wave coming out of it. No, nothing like that. This is a behavior where we find they are having the same kind of resistance. So XL is equal to XC. XL is what? Let us say the frequency at which resonance happens is omega naught L. This is 1 by omega naught C. So this omega naught will give us the resonant frequency. So we can say omega naught square is equal to 1 by LC. See, we are getting the same expression as we had in LC circuit. So we have omega naught is equal to 1 by root LC. Now don't jump into conclusion that every LC circuit will be a resonant circuit. No. So omega naught is 1 by LC. This is called resonant frequency. Now we can write this omega naught also as 2 pi f is equal to 1 by root LC. So f naught is equal to 1 by 2 pi root LC. Now how will you come to know this is also resonant frequency? This is also resonant frequency. They are all resonant frequency. From the question, how will you come to know the given, suppose that it is given that the resonant frequency is of some value. How will you come to know whether in the question it is this expression or this expression? To know that, we must have an idea of unit of measurement. This will be measured in hertz. This will be measured in radian per second. So students, please don't cram things, apply your mind. If it is given 50 hertz, then you have to take it this way. If it is given 50 radian per second, then it is this. That is exactly how. Small twist will be there in the question. Both are resonant frequency. This will be in radian per second. That is also frequency. This will be in hertz per second, cycle per second. This is also what is called resonant frequency. So in the numericals, series resonance, the key word will be there. Now when resonance is there, what will be, see, we got XL is equal to XC, na? See the features that we get. What we know, we also know Z is equal to root of R square plus XL minus XC the whole square. This is known to us. If XL is equal to XC, pass on this condition here. What do you get? This is called resistive circuit. We have seen inductive circuit. We have seen capacitive circuit. This is resistive circuit. Now in resistive circuit, what is the phase difference? 0. Phi will be here 0. How? See here. R by, see Z, what will be the value? XL is equal to XC. If XL is equal to XC, we get Z is R. Correct? Tan phi. You can find the value of Z is R. Na? Cos phi is what? Power factor cos phi is power factor. Cos phi is R by Z. Z is R. So from this we can say what? Cos phi is 1. What is the value of phi? 0 degree. See? So these are very important results. See, power factor is unity. How it will be expressed? 1. They will not give you cos phi is 1. It will be given in a circuit, the power factor is unity. This is one way of expressing. In another way, the power consumption and the true power are same. Then cos phi is 1. Na? P average is equal to ERMS, IRMS, cos phi. P average is the power consumption. ERMS, IRMS is power, actual power. They are equal. So cos phi has to be 1. See, so these are the ways by which series resonance, I can avoid the word resonance in the question, because the moment the word resonance appears, you know what kind of circuit it is. That is why, remember, if XL is equal to XC, then Z is equal to R. If XL equal to XC, then cos phi is 1. And the circuit will behave as a resistive circuit. See, these are the various ways in which the expression of tan phi XL minus XC by R can be analyzed. So that is exactly how we will be approaching the numericals also in this particular context.